All right. So in the last class, I was talking about stress concentrations. So, so what is going to happen in most of the design machine elements is that there will be certain regions within the part where the stress levels are going to be high. Such sort of points or such sort of regions where the stresses are high are referred to as critical regions, and the points where they are high are referred to as critical points. So so you are going to encounter so you're going to have critical points within your machine elements where the stresses would be high. So one of the reasons why stresses get high at critical points are the presence of features such as threads, steps, slots, okay, grooves. So presence of geometric features elevates the stress in their neighborhood. Okay. Now, broadly speaking, we will be concerning ourselves with uh, two kinds of stress concentration factors. So, stress concentration factor for normal components of stress and for shear components of stress. So, the static stress concentration factor for normal stress will be denoted as Kt, and static stress concentration factor for shear stress will be denoted as Kts. Okay, so Kt is basically static stress concentration factor for normal stress, and the Kts is basically, okay, static stress concentration factor for shear stress. Okay, static stress concentration for shear stress. So you will have Kt and Kts, and the way you define these stress concentration factors is, so for example, for static stress concentration factor Kt, we define it to be equal to the maximum normal stress divided by the nominal value of the maximum stress, and Kts is defined as maximum shear stress divided by the nominal value of the shear stress. Now, as I told you in the last class, this static stress concentration factor is applied only to brittle materials, and that too without any inherent defects. So when we are looking at static failure of materials, so static failure means failure due to a some sort of an event resulting in a large value of stress. Okay, so when we are looking at static failure from some excessive load acting at one point of time, then the stress concentration factor Kt will be applied only to brittle materials, that too without any inherent defects within the material. For everything else, okay, we take Kt to be equal to 1. Now that said, we are still interested in finding Kt and Kts for different kinds of geometric features because they will come in handy when we want to determine the fatigue stress concentration factor. Now, in order to understand how to determine this Kt and Kts and how to estimate the occurring maximum stress occurring at critical points, so consider this particular problem. Over here, what you have is you have a plate. Okay, so So here, what I am looking at is a plate. What I have is a plate. There is a step here. Okay. So I have something like this, and the plate is 2 mm thick. I have something like this. So the thickness of the plate is 2 mm. I'm not sure if you can see this, but the thickness of the plate is 2 millimeters. Let me make this a little bigger. The fillet is 1 mm radius. I am applying a force of 10 kilonewtons on this particular plate. On one side it is fixed. I have two geometric features in this particular problem. I have a circular hole of I'm looking at two instances, one where the circular hole is 4 mm and another instance when the circular hole is 8 mm diameter. And right, so the plate width at the higher thickness end is 40 millimeters and the plate width at the lower width side is 34 mm. So this is the problem statement. Now, I would like to know what is the maximum stress occurring within the plate for the given loading. So, in order to estimate the maximum stress, I first need to know what are the locations or what are the critical points where the stresses are going to be maximum. Now, in this particular problem, so based on those color contour plots I showed in the last class, the maximum stress would occur at these two locations. Okay, these two would be two critical points. I am denoting them as B and B dash, and the other two critical points are going to be A and A dash. Okay, so here and here. So these two are going to be another two critical points. So I have B, B dash, A dash. And because of the symmetry in the problem, I just need to bother about A and B. And okay, so how do we proceed? First, what you do is you determine something called the nominal stress. So if there was no stress concentration factor, then at B, okay, so whole location is B, right? So at B, what will be the stress? So what will be the stress? The nominal stress in the absence of stress concentration factor would be, so sigma naught nominal stress would be F applied, which is in this case 10,000 newtons divided by the sectional area. What is the sectional area? Total width minus the diameter of the hole, that is the region which is taking the load, multiplied by the thickness of the plate. So in this case, it is 40 minus 4 for the first case, multiplied by 2. So the nominal stress in this problem can be estimated as 139 megapascals. Now, once you know the nominal stress, what do you need to compute next in order to get the maximum stress at the, or in order to get the stress at the critical point B? What do you need to compute next? What do you need to?
Maximum stress.
You need to next compute
Stress
the stress
concentration factor.
concentration factor. So what do? You first go to the correct graph. Okay. So the graph I need to select would be the one where I have a plate with a hole which is being subjected to some far field tension. So this is the graph that I need to select. So let us say there is some particular curve. Okay, so you have this graph, and what does it depend on? The stress concentration factor Kt, uh, the stress concentration factor Kt. Now, in this particular problem, what is the nature of the stress? Is it a normal stress that we are looking at, or is it a shear stress? So as I am pulling on this specimen, okay, in the F direction. Now let us say my axes are, this is x1 and this is x2. So what kind of a stress am I generating in the material? In this x1
Normal
x2 it
stress.
Normal stress.
so it is, means the stress is predominantly normal stress, and that too sigma 1 1. So at the critical location B, which stress is high? Would it be sigma 1 1 or sigma 1 2 in the in-plane stresses? It would be sigma 1 1, okay, which is high. So the stress concentration factor you are interested in is Kt. Now what is Kt depending on? Kt depends on, so without even what do you think it will depend on in terms of geometric parameters? What are the relevant geometric parameters in this problem?
Sir, the width and the
And
diameter of it.
Diameter
yeah,
and the width. So what will it depend on? So you can see that it will depend on the ratio of the diameter of the hole to the width of the plate. Okay, it will depend on diameter, ratio of diameter to the width. So as the diameter, when will the stress concentration factor be highest? Interestingly, when is
ratio
it
when it is
highest?
smaller.
When the hole is actually smaller, the stress concentration factor is higher. It is a little counterintuitive. You would think that a bigger hole may result in higher stress, okay, but it does not result in higher stress concentration factor. You please make the distinction between these 2 points. So for and what is the highest value of Kt that you will get?
3.
The highest value of Kt will be 3.
0.02.
Okay, 3.0 or 3 will be the highest value of Kt, which is basically the problem of infinite plate with a hole being subjected to far field tension. Okay, that gives you a value of 3. For any other means for finite sized plates, it will always be smaller than this. So bigger the hole, smaller the value of Kt. Okay, now in this particular problem, so once you plug in the numbers, what you will find is that for the case when the hole diameter is 4 millimeter and width is 40 millimeter, d by w is 0.1. So for d by w of 0.1, kt is equal to, for d by w of 0.1, kt equals to 2.7. And for the case where d by w, where diameter of the hole is 8 millimeters, okay, so then in that particular case kt will be equal to 2.5. Okay, kt will be equal to 2.5. So for the first case, when d by w is 4 by 10 mm, what will be the maximum stress? Maximum stress will be equal to, maximum stress is equal to, so what is it? It is kt, which is 2.7 into nominal stress, which is 139 megapascals. So the end result is, the maximum stress is 275 375 megapascals. Okay, now when you have this 8 diameter hole, then kt is 2.5, but nominal stress is 156 megapascals. So what is the end result? The end result is sigma max for the 8 diameter hole is equal to 390 megapascals. Okay, so the stress is indeed higher for 8 diameter hole, but not by much. And also the stress concentration factor was actually higher for the smaller diameter hole. Okay, now coming back to this fillet. Okay, so until now we have looked at the maximum stress at the critical point B, which is just above the circular hole. Next, the next critical point will be at the fillet location. So for the fillet location, what is the nominal stress? The nominal stress is, for the fillet location, the nominal stress is sigma 0, which is the nominal stress is equal to applied force divided by cross sectional area, which is 10,000, which is the applied force divided by the the smaller width, which is 34 mm, multiplied by the thickness of the plate, which is 2 mm. So sigma naught is 147 MPa for this. That is the nominal stress. And then in order to get the stress concentration factor, we have to go to the stress concentration plot, which looks like this. Okay, where basically what you are doing is you have a plate with a fillet over here. Okay, so you are looking at a plate like this. And then what are the geometric parameters? You have three geometric parameters now. What are they? You have the bigger width, smaller width, and the fillet radius. So you need to select the curve corresponding to some capital D divided by small d, which matches with what you have. And then you estimate KT for the given ratio of the fillet radius to the smaller width. Okay, so in this problem, what do you have? So capital D by small d, what you have is capital D by small d is 1.18. The fillet radius to small d is 1 by 34, which is 0.026. So based on this, you can estimate that the stress concentration factor is 2.5. Once again, it is a normal stress which is appearing over here. So what is the maximum stress at the fillet location? It is actually equal to stress concentration factor multiplied by nominal stress, which is 368 megapascals. So for the case where you had a 4 mm dia hole, where is the stress higher? Is it higher at the hole or is it higher at the fillet? So at the hole it was 375, at the fillet it is 368 MPa. So they are actually very close. So it is still higher at the hole, but means they match up quite well. Okay, now see, hole diameter you can't really change because that will be decided by the application, but fillet is something that you can play around with. So if you want to reduce the stress at the fillet, what is the simplest solution?
Increase the
You can simply increase the fillet radius. Okay, so if I doubled the fillet radius, what would have happened? So if I had gone to fillet radius, if I doubled the fillet radius, then my stress concentration would have dropped to maybe somewhere around 2 or even less than 2. So means you should always use the highest fillet radius which is possible in your application in order to reduce the level of stress. Okay. Next, so that is about stress concentration factors. So what you need to do is you need to identify the critical points in your problem. Then you need to figure out what is the nominal stress at the critical point, and then using an appropriate graph, you need to find out what is the corresponding either static stress concentration factor or uh, in KT or KTS, depending on whether it's a normal loading or a shear loading scenario. You have to pick one and get the static stress concentration factor. The product of the two, nominal stress times the stress concentration factor, will give you the peak stress. All right. Next,
Sir,
so
sir, I
yeah.
have a question. If we have that hole in proximity of the fillet, so in that case, how would we calculate stress concentration factor?
So if you have a reason to believe that you have coupling, Okay, means you cannot look at each feature in isolation. Then only way to deal with it is just go ahead and set up a finite element analysis simulation and estimate the stresses.
Okay, sir.
uh, just a heads up that the finite element analysis for structural analysis is very straightforward, means as long as the geometry means it's very straightforward. So FEM is always a way out. If your graphs are not applicable in a problem, you can always use finite element method in order to get your peak stresses. And in fact, if you use FEM, you basically get the stresses at all locations within the part, not just at the critical location. All right, next. So geometric features are,
Hello, sir.
yeah.
Hello, sir. I have a question that you said that if we increase the fillet radius, the stress concentration factor will lower the
Yes.
KT. So why do you use the fillet? We can just use taper surface. Then the radius of curvature will be infinite, and there the
No,
stress
so
concentration
no,
factor.
your thinking is wrong. No? So even if you use a taper, so let us say you have a taper. Okay. So this is one section. This is another section. You are saying let's do something like this, right?
Yes,
Now,
sir. Yes,
what
sir.
is the radius of curvature here? Taper does not eliminate the uh, radius of curvature. You will always have a fillet because the tool has a certain tool radius. Okay, whatever you do, you will have a fillet. It is just the question of what is the fillet radius. Okay, so see,
Sir,
there will
for
be
every
steps
edge
in
we need
shafts.
to have two fillets, right?
What is it?
For every edge we need to have two fillets for the upper edge and the lower corner.
Upper one won't matter. The lower one is more critical because nominal stress is higher for the lower one.
Okay, sir.
Okay, and also something interesting happens if you have means if you have noticed the FEM result. Na, what happens is, so if you have something like this and you pull on this, there is a dead zone which gets created. Actually, in this region there is no stress in the material. It's called a dead zone. You are unnecessarily wasting the material there if you have a step. Anyhow, let's move on. Now, in addition to geometric features, another reason why stresses can be very high at some locations within the components is contact. Contact is whenever two parts are contacting one another and there is a load transfer happening across the contact, uh, the stresses in the contact region are typically very high. Can you give me some examples where you have contact across elements in machine design?
Gears,
Yes.
Okay, gears, very good, good example.
sir, cams,
Gears, cams.
belt, and
No, belt is not so much really, means belt it gets spread out.
Sir, bearing.
Bearings, okay, bearings. Anything else?
Sir, mechanical joints such as screws or
Mechanical joints, okay, one of the most important things. You have some kinematic motion, you will have a joint and there will be contact. Okay, anything? And then any rolling element basically. Okay, there will be contact. So there are several places where you have contact across parts. Uh, okay, and at all these contacts you should be worried about the contact stresses as to what they are going to be. Now, Hertz was the first guy to come up with the means to solve problems in contact mechanics and come up with some nice closed form results for what will be the size of the contact and what will be the stresses in the neighborhood of the contact. Okay, so that's the reason that for elastic contact we refer to elastic contact as Hertzian contact. Hertzian contact. Okay, now if you have two spheres contacting one another, then in that particular case it can be shown that the what will be the shape of the contact patch if you have two spheres which are contacting one another. What will be the shape of the contact zone?
Circle.
Circle.
It will be circular.
Point.
Okay, so contact zone or contact patch is circular in this case. So the radius of this contact patch, the radius of the circle is given by this expression. Okay, so we are not going to get into derivations, it's pretty complex. So this is the radius of contact, and what you have is you have a parabolic distribution of contact pressure within this contact patch. Pressure is highest at the center of the contact. So the nominal pressure, the average pressure, what is the average pressure in the contact zone? What is the average pressure in the contact zone? P average, what is it?
F
Come
by
on.
F
F
by
by
A, area
A.
of the patch.
Area of the patch. What is the area of the patch?
Pi a square.
It is
Y
pi
square.
a square. Okay, so average pressure in the contact zone is F divided by pi a square. So you have a parabolic distribution, and in a parabolic distribution, what is the relation in a parabolic distribution with pressure being 0 on the outer edges and cross section being circle? What is the relation between maximum pressure and average pressure? You have this for velocity also, no? Laminar flow. So what will be P max if it is parabolic distribution? It will be 3 by 2 times P average. Okay, you remember you have the similar relation for velocity when it comes to laminar flow in a pipe. Okay, so anyhow, so you have this. Now just to see like what is the contact patch size, and then what is the kind of pressures which get generated. Okay, let me change the screen. Okay, so you can see my screen, right? So I don't know how many of you are familiar with symbolic manipulation softwares. How many of you have used Mathematica before? Okay, fine. So see, Mathematica is a symbolic manipulation software, meaning that what you can do over here is you can you can write analytical expressions without defining the variables, and then you can do manipulations. So what I have done over here is I have chosen some parameters corresponding to that of steel. Okay, so what is the modulus of steel? It is 200 gigapascals. What I am doing is I am assuming force in newtons and length in millimeters. So these will be the basic units I will work with. So if force is in newtons and length is in millimeters, Young's modulus will be, what will be Young's modulus? What will be the unit of pressure then, or stress? See, force is in newtons and length is in meters, then
Megapascal.
stress will be in pascals. If force is in newton, length is in millimeters, stress will be in megapascals. So E I am writing as 200,000 megapascals. Poisson's ratio is 0.3, it is unitless. I am taking 10 millimeter diameters balls, spherical balls made of steel, and I'm applying a force of 100 kg. Okay, it doesn't look big for steel, so I'm applying 10 kg force. Okay, now I'm applying this formula which I have just given in the notes. and I'm also estimating the maximum pressure. Okay, so let us just estimate this. So shift enter will estimate the two of them. So what is the contact patch radius? So the length is in millimeters. I just told you, right, that the length is in millimeters. So what is the contact patch radius? A is the contact patch radius. So what is it? I've just printed out the result. No, just repeat it.
0.119.
What is the unit? Always say the units. Without units, never say the units.
0.119 millimeters.
So 0.119 millimeters or about 120 micron. Okay. And what is the contact pressure? What is the maximum pressure?
Three thousand three 343 megapascals.
Megapascals, or it is about 3.3 gigapascals. Okay. Is it a surprising result? It is a steel ball. Application of 10 kgs on a steel ball doesn't look like much, does it? But
No, but
what
like the contact patch is
Mm.
so less that the stress
but
can
the
be.
contact area is so little. Okay, it is just about 120 micron. It is so little that basically the force is getting applied on a very small area, and consequently the contact pressure is very high. Okay, so this is a feature of contact, that because steel and metals in general are very rigid, the area across which the contact patch forms is normally very small, particularly for non-conformal contact. And because of this, the stresses in the neighborhood of contact are typically very high. And if at all there is a failure, that is one location where there is a high possibility of failure at the contact. Now let me move on. Again, I'll come back to this screen. Okay, now moving on. So fine. So this is just for the contact pressure. Now you can also determine the other principal stresses. So if I assume axis like this, that the contact plane is formed by x and y axis will form the contact plane, and normal to the contact is along z direction. Okay, so the three principal stresses will be will be sigma 1, sigma 2, sigma 3. Now you can plot the three principal stresses as a function of depth. Okay, you can plot sigma as a function of depth. So what do you see? So this is sigma 3, this is sigma 1 and sigma 2. So now and this is tau max. Okay, so this over here is tau max. So what can you say about the either the maximum shear stress or von Mises stress? They're very close. Maximum shear stress is very close to von Mises stress on the surface as a fraction of the contact pressure. What can you say is the shear stress and the von Mises stress? It is only a small fraction of the um, maximum pressure on the top surface. Now where is the shear stress maximum in the material? So if I look at shear stress as a function of depth, what do I find? It actually increases as I go inside and then starts to drop. Where is it maximum? So it is maximum at a depth of about 0.5 times the radius of the contact patch. Okay, and what is the value at which it is maximum? It is about 0.3. So in the problem we have just solved, what would be the maximum one shear stress? it would then be about how much? About 1 GPa at what depth?
At 60 microns. Oh,
At about 60 microns from the top surface. Okay, so the maximum Mises stress or maximum shear stress occurs at a depth of around half of the contact patch radius for the circular contact. Okay, now there are also similar expressions for cylindrical contact. Okay, and in the cylindrical contact, well, this is the, so what will be the contact patch shape for cylindrical contact?
Rectangular.
Line.
Rectangular. Okay, so contact patch shape is rectangular. So if it is rectangular, what will you have? You will have length of cylinder, and then you will have semi width B. Okay, so what is the nominal area? Nominal area is actually F, means nominal pressure is F divided by B into L, and the sorry, F divided by 2 into B into L. Okay, and the P max is 2F by pi BL, where B is given over here. Okay, now B is given over here. I'll give you some problems on this later on so that you get a better feel for this. So once again, what I want you to sort of pay attention to is this graph of how the stresses vary along the depth. So this is the depth direction. Once again, you see the maximum shear stress is not on the surface. This is for pure rolling. Okay, means there are no shear stresses on the top surface. You are only applying normal load. Then in that case, maximum shear stress happens at a depth of about 0.8 times the semi width of the contact. Okay, so, and what is the maximum shear stress? It is once again equal to 0.3 times P max. So in railways application, for example, this semi width is about 6 to 8 millimeters. Okay, and contact patch is, think of it as circular, nearly circular. It is elliptical, but let's say it's close to the circle. So if it is 6 to 8 mm, at what depth will the von Mises stress be highest? Give me a rough number, no?
2
3
mm.
millimeter.
It will be highest at about 3 to 4 millimeters. Okay, so one major implication of this is whenever you are looking at a fatigue failure, the failure will get initiated at the location where von Mises stress is highest. So in railway application, rolling contact fatigue failure gets initiated from underneath the surface, not on the surface. Cracks will originate at about 3-4 millimeters depth inside the material, and then they will come to the surface. What will happen in such sort of a scenario? If cracks originate on the inside and then come to the outside, then what will happen? It will take out a chunk of the material. Okay, so it will result in pitting failure. This is similar to what you see on roads also. You will see that roads many times when they get damaged, what will happen? You get this pit formation, right? Instead of surface erosion, you get pit formation. So in this rolling contact fatigue failure, what you have is pitting of the material. Cracks will originate from inside and then they will grow out to remove a chunk of the material. Okay, all right, so I have more things, but let me stop here. I am going to share that Microsoft form with some questions. Give me 2 minutes. In the meanwhile, if you have any queries on what we have covered today, you can ask. All right, today I just have only 3-4 questions for you, so finish it off quickly. Okay, so finish it off by the end of class. All right, I have just pasted the form link, so finish it off in 10 minutes. Do not take more than 10 minutes.
Sir,
Yeah.
sir, do we decide the depth we need for the surface hardening using this analysis?
Yes, this plays a very important role. Yes. So wherever the stresses are high, you want to harden the material. You're absolutely right. That was a very good insight from you. Yeah.
Sir,
Yeah.
can you go back to the like the graphs of the stresses and can you highlight the sigma and sigma 2 stress? It wasn't visible clearly.
Which one are you talking about?
Sir, the graphs of stresses
Graphs of
at the contact,
stresses at the
like
contact.
sigma and sigma.
Hmm. Yeah. So this is spherical contact. Yeah. So let me use different colors. So the pink one is sigma 3. So this is sigma 3. Okay. Then meaning along the z direction, along the depth direction. Okay. And then the orange which I'm drawing now is for sigma 1 and sigma 2. These are in plane stresses. Okay. So stress is mostly hydrostatic in nature on the top surface at the center point. All of this is at x comma y equal to 0. Meaning
Okay, so the won't it vary with x and y?
it will vary with x and y. You need to look at some 3D contours, color contours if you want to see everything. This is just a
Okay.
line graph at x comma y equal to 0. You are going along z and you are seeing how the stresses are varying. Why are we looking at this? Because this is the line where the stresses will be maximum.
This is for the spherical, right?
Yes, this one is for the spherical contact, right?
And the failure occurs due to the shear stresses always, like because the sigma 3 is highest at the surface.
No, I did not say failure occurs. I said if the failure occurs because of the if there is a ductile failure in the material, then I said failure originates subsurface. See, if you have done a good design, if you have chosen a strong enough material and if you are applying low enough loads, then you will not have ductile failure or you will not have this subsurface failure. You may just have wear and tear on the top surface. But if your loads are high and you do not have sufficient strength, then you can have rolling contact fatigue where cracks will originate from underneath the surface and grow out to remove a chunk of material. I can in fact show you a picture.
Or by rolling contact here we mean the spherical or the cylindrical one?
It is normally neither. It is basically contact between two bodies. Like many bodies are neither spherical nor cylindrical. Spherical, cylindrical are chosen because analytical expressions are simple. Take this rail wheel example. Okay, so you have two sets of curvatures for. See, this is what I meant. You can see the chipping, na? So this is rolling contact fatigue failure. You can see this. Well, you can see the shelling, na? Where I have written wheel shelling. You can see the. No, I can't write on this, but you can see the shelling. By the way, these ones are Rajdhani wheels. So Rajdhani trains have this big problem of wheel shelling because they move at higher speeds, there are higher dynamic loads, and material fails.
Sir, here we have assumed the contact to be frictionless, but generally the contact has quite a decent amount of friction if proper
No,
lubrication is.
in most of the contacts that you deal with are very low friction.
Due to
So
lubrication.
means,
Hi.
sorry.
We do a heavy lubrication in order to reduce friction contact. No?
It could be that. So if you take bearings, for example, they are designed to be nearly frictionless. Okay. If you take this rail wheel contact, most of the, except for locomotive wheels, none of the other wheels actually have any motors or traction being generated. So it's near pure rolling condition. If you take pin joints, for example, so in majority of the joints, you would want it to be frictionless. Okay, and where you do have friction, it is still only a small fraction of the normal load. Like the apparent friction coefficient means shear force divided by normal force. In majority of the applications, you do not try to extract more than 0.05 or zero point 0.1. So it is still the effect, the stresses are predominantly still coming from the normal force or normal stress.
So for finding the stress concentration factors, we use the graph for the features, right? So for different materials or let's
Right.
say like
I
contact between
told
hybrid
you, right?
materials.
You can either use the graphs or you can use finite element analysis. You can use both of them.
Okay, so for like the newer materials or not so common materials, we use the
It has got nothing to
analysis.
do with materials. It's not much about materials. It is more about geometry and loading.
Yeah, we discussed that. Yes.
Huh.
So in case of the fillet, which we first discussed,
Uh-huh.
uh, while calculating the area of cross section, in calculating the nominal stress,
Mm-hmm.
uh, We wrote the area to be 40 minus 4 whole square, right?
Not whole square, into 2. The thickness was 2 mm.
Sorry. Okay, sir. Thank you. I was confused.